להנמיך. I'm going to be a little slow today because I just taught for 4 hours. But it's okay, this is the slow part of the course. So after we had motivation for why we want general relativity as a geometric theory of space-time and its relation to mass and energy, and we came to the conclusion that we need to talk about a differential geometry. Today we're going to do the math and define a little bit of the beginnings of what is differential geometry. We're going to start with better formulating the notions you know from flat spacetime in terms that we will be using it on curved spacetime. So we're going to start with a reminder: physics in flat spacetime. Flat spacetime. In other words, special relativity. Okay. If someone doesn't have a good basis in special relativity, you can read Asaf's lecture notes from Mechanics and Special Relativity, or any other basic textbook, or the course we have here on modern physics. The principle that we wanted to use, that special relativity was based on, was of course the equivalence principle, the laws of nature are invariant in all inertial reference frames. Among which the speed of light c, speed of light c is constant. One of the laws of nature is that the speed of light is constant in every reference frame, and as we already mentioned, this defies the Galilean expectation of, for example, addition of velocities. If we have a system O and a system O prime, and the velocity u here, which should transfer to u prime here, if there's a relative velocity v between them, then the naive Galilean expectation that u plus v equals u prime, or in this case minus v, going in that direction, this can no longer hold. This is only a limit of what we need to do, which is develop the proper transformation between two reference frames, which would be the lowest transformation. And as you might recall, we derived that by considering a source of light in the system O at 0, 0, 0, and we can also call the time 0. And now a sphere of light is extending outwards, and at any point x, y, z, t in the reference frame O, it has to hold that x squared plus y squared plus z squared equals c squared t squared. That is the definition of the velocity in Euclidean space. This is flat. Has to be c times t squared. C times t. The distance traversed is at velocity c. And this has to hold in every reference frame. So each one of these coordinates might change, but the overall invariant will remain x prime squared plus y prime squared plus z prime squared equals c squared t prime squared, and there is no prime on the c. The velocity c is invariant. Okay. If we have any other two events, this is just a specific example, we can have any two events in space-time. So event is in space-time, it has 4 coordinates. we can have the interval. So now we'll have this general x1, y1, z1, t1, and here we'll have subscript 2. Then the interval will be conserved. So this will be delta x squared plus delta y squared plus delta z squared minus c squared delta t squared. This is called the interval squared. Interval squared, and again in this case it's given in the space form, so it's positive, or it goes like x. X, y, and z appear positive. Delta t appears negative. This you can all call delta r squared. So the convention here for the interval space is squared space is positive and squared time is negative. And of course, this concept of an interval that's conserved is very, very similar to the notion of distance that you know from two-dimensional Euclidean space. That is, if I have x, an x and y reference frame, and then I keep the source, the origin at the same place, but now I have, say, I rotate x here by alpha, and I keep them perpendicular. So this is alpha, this is now y prime, and x prime. Then any point here, xy, I can also expand or describe as x prime, y prime. Or if you want, if I look at an interval, then this distance will be delta x, this distance will be delta y, this will be delta y prime, this will be delta x prime, and we immediately see that delta x prime is longer than delta x, delta y prime is shorter than delta y. So no coordinate is conserved, but of course the distance, which is the length of this vector, delta s, is conserved. Because of course delta s, you will think of it as the how do you say yeter in English?
Distance?
No, yeah.
Hypotenuse.
The hypotenuse. The hypotenuse squared can be described in the black triangle as delta x squared plus delta y squared, or I can describe it as a hypotenuse in the right angle triangle in blue, delta x prime squared plus delta y prime squared. And of course, this is what we call in geometry just the distance. So this rotation conserved the distance. The distance is said to be invariant in complete analogy. Okay. Implied here is a metric. Implied here is the metric 1, 1, 1, the Euclidean metric. Which means that you define the interval, in some sense as multiplying a column vector, which in this case is delta x, delta y, through the metric 1, 1, 1, and so the row vector times the column vector.
It's
0, 0. Sure. Or if you really want, you can have a z. I can rotate the angle in any number of dimensions, as long as I maintain that it's flat and Euclidean. Okay. So of course we're going to generalize this concept to 4 dimensions to events in space-time. And then we'll need to generalize our still flat metric, but now it's going to be Minkowski flat rather than Euclidean. So we will define our vector, 4 vector x mu, to be the vector x0, or I should put it on top. From now on, I'm actually going to care about whether the indices appear at the bottom or at the top. So take notice. x0, x1, x2, x3. I define this to be CT, x, y, z. Okay, so the 0 coordinate, to keep my dimensions consistent, it's c times t. And sometimes we can also shorthand this to CT xi. So mu and general Greek indices will go from 0 to 3, indicating t, x, y, z. There will be 4 of them. And Roman or Latin indices will only be space-like. 1, 2, 3. Okay, so if you want, this can also be written as x0, xi. This distinction is sometimes helpful because you know that 4 indices are full space-time, and space is kind of simpler. We want to do, for now at least, this is even the Euclidean part. Okay, so our metric will not be 3 by 3, it will be 4 by 4. It's called eta mu nu, the metric of special relativity, -1, 1, 1, 1, and these are all zeros. And then, of course, in the language of the interval, delta x squared is multiplying this vector as a row vector through the metric by itself as a column vector. So we'll have x0, x1, x2, x3, -1, 1, 1, 1, 0, 0, x0, x1, x2, x3. This is a very inconcise notation, but what this actually means is that I'm summing over all mu and nu, each going from 0 to 3, 0 to 3. And of course, it's a matrix multiplication, so eta mu nu, x mu, x nu. And now we have Einstein's summation convention, which tells us every time an index appears double, once up and once down, and it will consistently always have to be once on the top, once on the bottom. That basically implies that what we were doing here was multiplying, for example, a matrix by a vector. So we were summing really over all of them. So we define, this is just eta mu nu, x mu, x nu. That is, we don't bother describing the sum here. If we put the double mu index and the double nu index, that means we're summing over all, in this case, 16 options for mu and nu. Why 16? Because they're Greek indices, so each of them get 4 options, times 4 is 16. This and this mean exactly the same thing. The summation is implied. Okay, so that's Einstein's summation convention. This, of course, just a reminder, is completely identical to what we started with, delta x, or x squared plus y squared plus z squared minus c squared t squared. This is just a matrix notation for the exact same calculation. Questions up to now? This should be familiar. A Lorentz transformation, then, will be a transformation from one coordinate system O to another one O prime that conserves this interval, this delta S squared. And we want to talk about all the possible transformation that maintain this interval. So let's write that down. what are all the transformations which conserve the interval. And I'm going to make one slight modification here. Because I wrote this as an interval, it's implied that I have two events. And so I'm actually calculating this on the delta axis. Delta, 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 and delta. Okay, so what can I do to my frame of reference that will maintain the interval unchanged?
You can rotate the spatial axis.
I can rotate the spatial axis. So I have rotations. In GR we call them spatial. Not spatial as in special, but spatial as coming from space. Spatial rotations. How many of these do I have? This will be a group of rotations, right? Which has three generators. Because I can rotate around X axis, I can rotate around the Y axis, I can rotate around the Z axis, and I can compose my any rotation with those. But it's not particular notation. Okay, let's call our rotations. What would be a good letter for them? Let's say R. Big R. These are matrices which will generally look like not changing anything in time. 0, 0. In the spatial part, okay, we're gonna have three of them. So our X will be something like Z is maintained. X is maintained. And here I have some cosine theta minus sine theta, cosine theta. And I'm going to equivalently have Ry and Rz. And I can multiply them, that is, apply them in succession. And maybe an important thing to say is that they do not commute. Okay, so the rotation group is non-commutative. It's not abelian. Right? Rx, Ry minus Ry, Rx is not equal to 0. What is it equal to? It's some product of Rz. Right? There's an anti-commutation commutation relation here, which you explore a lot more in quantum mechanics. Okay. Why are spatial rotations a subset of our Lorentz loop?
It doesn't change the state.
They don't change. They don't do anything to the time. They only mix up the space, but they change the space, which is Euclidean, in what we already saw was the Euclidean transformation, just rotating the axis. So delta R doesn't change. The delta T doesn't change. So of course their difference doesn't change. Okay, so we have spatial rotations. Yes.
You can rotate also with the T direction, the hyperbolic rotation.
Exactly. So this is what we call Lorentz transformations, or boosts.
Also like that's exactly.
Yes. So we have boosts. Boosts, which are kind of time-space rotations. Also, this is what you learn in modern physics as Lorentz transformations. It's really just the boosts, Lorentz transformations. And those we usually mark with a lambda. Lambda mu prime nu. that is x mu prime equals the transformation times x mu. Again, I have a vector multiplied by a matrix, giving me a vector, and it's implied that I have summation over the new coordinate. And what do these matrices look like? So now, for example, a boost in the x direction, so I'll call this lambda x. Not to be confused with the Freemasons. This is just a lambda with an x on top. I'm going to have some cosine omega minus sine omega minus sine hyperbolic sine omega cosine hyperbolic omega 1 1 0 0. Okay, this is a boost in the x direction. It kind of rotates t and x, but it's not an antisymmetric. It's not an, the off diagonal doesn't have a minus sign. It's minus and minus, or if you want plus and plus. And these are hyperbolic rather than normal trigonometric functions. There was a question on the back there. Okay, hyperbolic. Okay, so we have spatial rotations and we have boosts, Lorentz boosts, or if you want Lorentz transformations. And what else do we have? Translations. Translations. Typically, people start with these. They're the easiest. X mu goes to x mu prime, which is x mu plus some constant a mu. And of course, it's trivial to see that these conserve the interval, because in the interval, you take the difference between two x's, delta x mu prime will be x mu plus a mu 1 minus x 2 mu plus a mu 102 here. Now these cancel out, so this is x1 mu minus x2 mu, which is just exactly delta x mu without the prime. So in this case, each one of the four coordinates is not changed, so of course the interval is also conserved. That's just a shift in the origin of our spacetime. Okay. So we had rotations and we had translations. To be fair, these rotations are also 4x4 matrices, so I can maybe maintain the same format. I'll put the x on top, the y on top, and the z on top, and I'll keep the mu prime nu, mu prime nu, mu prime nu. You'll also notice I write the upper index slightly to the left of the lower one. This is very comfortable when you have a lambda because it forces you to do it. If not, for R, for example, you leave a little space. That's because while it might not matter or appear to matter at this point, later on the order of the indices for various tensors, which these are going to be, a subclass of, the order is going to matter. So you can jump between the up tensor, the up indices and the down indices, but maintain the order. So keep some space in between. Okay. So other than the translations, basically all of our transformations are x mu prime equals some matrix. I'm going to use this lambda again, but now maintain that it can be either a Lorentz boost or a spatial translation. Yes?
Is the group of Lorentz boosts generated by the three Lorentz boosts above the axis?
Yeah?
Is the group of Lorentz boosts generated by the three Lorentz boosts about the axis?
The different axes?
Yeah.
Yes. Yeah, so,
like the rotation group is generated by the three rotations about the three axes. Is the Lorentz group generated by the same?
So, are you asking if it's closed?
Not closed, but we had the group of spatial rotations being generated by the three rotations about the axis
Yes.
is the group of Lorentz.
So is this group of generators enough to generate the whole group?
Yeah.
Okay. So two funny things happen. The first is that if you only look at Lorentz boosts, it's actually not a group. That is, it's not closed. Because the commutation of two Lorentz boosts, say in the x and y direction, is not a boost in the z direction. It's a rotation in the z direction. Okay? So here lambda x, lambda y, minus lambda y, lambda x, will actually give you another RZ. So if you want to look at it in a groups language, mathematically, you need to look at the group of rotations and boosts, and then you have a group. And you have 6 generators. That is the 3 rotations and the 3 boosts about the axes. And that group is closed under multiplication.
And it is a subgroup of the whole.
No, it's the opposite. The spatial rotations are a subgroup of the Lorentz group. Which subgroup? The ones that does not involve time. So it's a closed subgroup. Yes.
If you only have Lorentz, the gamma x, the lambda x matrix, and spatial rotations, you can also generate the other. Like take all the
Yes.
spatial rotations
Yeah.
and one of the Lorentz. So you
Yeah. Basically, what you're going to do is probably what you want to rotate your system to whatever you want, and then rotate back. Okay. So we have 6 degrees of freedom in our allowed transformations, in our allowed Lorentz transformations, plus 4 degrees of freedom from translations, which again can be, this is a 4 parameter family, because we have 3 spatial ones and 1 time. So that gives us to a total of 10 members of the group. Okay. Okay. Let's explicitly check that some of these things maintain the interval. And I'm just going to write the explicit equation. What we are demanding, delta S squared, equals eta mu nu delta x nu delta x nu. If I'm saying that I want to maintain the interval, then I'm saying that if I apply one of these matrices, I'm going to have an eta mu nu. Maybe we'll do it this way. Let's look at the new, not the new system in terms of the old ones, the old one. So I'm going to have here eta mu nu prime. This is going to be lambda mu prime sigma delta x sigma, and this is going to be lambda mu prime rho delta x rho. And now grouping them together, I'm going to have eta mu nu prime lambda mu prime sigma sigma lambda nu prime rho delta x sigma delta x sigma delta x rho. And now this is of the same form. If I want this to also be flat Minkowski space, that means that this is just equal to eta mu goes to sigma, so eta sigma rho.
Yes, the mu and u, when you put a tag on the nu, on the eta,
Yes,
means that
you should have one here, here, and here.
also in the first and second.
And here, and here, and here. Yes. Okay, so this is another way to think of what these the allowed transformations are. They are the transformations that keep my metric itself as the same tensor, or invariant. That is, they keep eta sigma rho equal to eta mu prime. Mu prime lambda mu prime sigma lambda mu prime rho. How many equations are hiding here? 16. This is a 4x4 matrix. There are 16 equations. Yes, most of them are trivial. Or that is, if you know how to choose your lambdas, then you'll find that most of them are trivial. So let's look at one example. Let's look at.
Wait, but translation is the law.
The translation is not.
This form.
Yeah, I couldn't even write it in this form, right? I had it plus a constant. So this is just the Lorentz group.
Also rotation on all Lorentz.
Also rotations. This is the Lorentz group, to be closed, includes rotations and boosts. The group that includes also constant translations is called the Poincaré group. Okay, so Lorentz group, you have 6 generators, 3 and 3, plus translations, that's 4, equals the Poincaré group. Poincaré. Okay. So, for just an example, if we wanted to look at, say, rotations about what we had there, the x-axis, and let's look, for example, at eta. Which one will we want? Let's take, for example, rho equals sigma equals 3. I want to look at the z component of the metric. So it has to be 1, right? If this were 0, it would be minus 1. If it's 1, 2, or 3, then it's plus 1. That's eta 3, 3. And so by definition, this has to be eta mu prime, lambda sigma is now 3 mu prime, and lambda mu prime is here, and rho is 3. I have to now sum over all 16 combinations here, but most of them are trivial, because if I go to lambda and I look at the third column, that is actually number 4, I see that if mu prime is either 1, 0, or 1, it's 0. It only leaves me with 2 and 3. Of course, this is diagonal. So basically what this leaves me with.
About what Lorentz transformation you're talking about?
Now I'm, for example, looking at this rotation. Okay, so let's now say this is Rx. And it appears twice. Okay, so this is diagonal, so I'm going to have lambda 2, 3 times lambda 2, 3 plus lambda 3, 3 times times lambda 3, 3.
Does any other combination of mu tag and mu tag is 0?
Was this everything I wanted?
Yeah, and it's sign.
Yes. All the others are 0. Okay. So now 2, 3 is going to be 1, 2, 3 sine squared minus sine some angle squared plus cosine of that angle squared, and this is indeed 1. So that checks out. Yes.
Is the top index the row or the column?
What?
Is the top index the row index or the column index?
So if you multiply this, so if you have just a vector like this would typically be the column index, the column vector.
Okay.
So that's the one you multiply on the right.
So,
Yeah, but for now, so it will change soon.
okay. This is not reassuring.
Okay. The reason I'm having a trouble with the question is that we very quickly stop talking about matrices and just look at the tensors. Because, you know, obviously here you have one at the top and one at the bottom, so it's easy. But very soon you'll have 2 at the bottom, 3 at the top, and such. So left and right is kind of, they lose their meaning. What? No. We just have to give them up different names. We have to maintain the order and remember who's on top and who's on the bottom. And then it's consistent. Okay. We can of course repeat this exercise for another one. Let's do now a Lorentz boost. If now we want to do a boost, let's take an interesting one, say -1. So let's look now at rho equals sigma equals 0. This was a rotation, and now we're going to have a boost. So I want eta 0, 0 to be -1. And by definition, this is going to be eta mu prime, lambda now going to have mu prime 0, lambda mu prime 0. Okay. Which of these can be non-zero? So this of course is diagonal. So mu prime has to be equal to nu prime. Which then have 0 component, either 0 or 1. So I'm going to have eta 0, 0, lambda 0, 0, lambda 0, 0, plus eta 1, 1, lambda 1, 0, lambda 1, 0.
We left in the left, it's eta, in the right, it's eta prime. Like.
On the, which left?
Because you calculate eta 0, 0, and you use eta 0.
Yes, these are primes. Okay. So now this, of course, is -1. This is +1. This is going to be cosine, hyperbolic cosine some w squared. This is going to be hyperbolic sine of w, some w squared. And together I have minus cosine squared plus hyperbolic sine squared, which is minus. Okay, so these check out. Okay. There are other transformations one can consider that maintain the interval. They're less interesting to us in this course because they are not continuous or differential translations or transformations. For example, I can consider flipping the direction of time. I take an event, I flip t to -t. Because the interval only has the t squared, c squared, t squared, delta t squared, it doesn't matter if you flip the time direction. It also doesn't matter if you flip any of the spatial directions. You put a mirror on space-time, the geometry doesn't change. So these parity and trine reversal symmetries are symmetries that maintain the interval.
Then your system is not right-handed.
Yeah, by definition, if you flip, it's not right-handed. So the interval is maintained. That's what we wanted. So we're not going to bother to write them, but know that they exist. They do have meaning in particle theory, particle physics. Some of you might have seen pair. Well, you saw them. We won't talk about them anymore. Okay. Of course, one can write this equation with this lambda, a boost in the familiar form. If we now kind of go back and ignore the matrix notation, and we just have that ct prime is ct cosine of some angle minus x times the hyperbolic sine of that angle, and similarly x prime is ct minus ct sine hyperbolic of some angle plus x cosine of that angle. this is how many people start by learning the Lorentz transformation, but it's just, it comes from the first trigonometric hyperbolic identity, which is the conservation of the interval. And if you want to look at the velocity for the point for which x prime is 0, then you have from x prime equals 0 that ct hyperbolic sine omega is equal to cosine hyperbolic of omega, and so ct, wait, did I flip something? What did I flip here? Ah, yes, I wanted x. I wanted this to be 0, so I need an x here. Good. And now x divided by t is c sine hyperbolic divided by cosine hyperbolic, is hyperbolic tangent of omega, and then this we call beta, and c times beta is just v. So these are the familiar definitions. We can also calculate 1 minus v squared to the minus 1/2. In hyperbolic geometric terms, this means 1 minus v over c squared. This means 1 minus beta squared minus half, so it's 1 minus hyperbolic tangent squared omega to the minus half. We have an identity that tells us that this is just 1 over hyperbolic cosine squared of omega to the minus half. That's just cos omega, which you know as gamma. So that's the relation to what you know. And of course, that means that you can innocently write the transformation as ct prime equals gamma ct minus gamma beta x, and x prime equals what we have here, gamma x minus gamma beta t. And how many c's do I need here? I need 2 of them. Gamma x minus,
You need 1 C.
no, 1 c. 1 is enough. But here I need another division by c.
No. C times.
Okay, I multiply by it? That's fine. Good. Questions up to now? Okay. So now we have all these classical special relativity effects, like time dilation. That is, if I look at the frame of a particle, its own rest frame, then delta x, delta y, delta z are 0. Only delta t is different from 0 because nothing can stay in time. This will be some dt. And this will be now called proper time. And it means that I can also call it d tau in this case. And now d tau squared, or delta tau squared if you prefer, is going to be minus delta s squared over c squared. The opposite convention, where delta s squared is just x plus y plus z squared, all of them are 0, minus c squared d tau squared dt squared. So the two minuses cancel out, and this is the relation between the terminology of proper time and the interval. And by definition, this is 1 over c squared, eta mu nu, delta x mu, delta x nu. And this now has to hold in every reference frame. Okay. Which means if we now have a moving clock with delta t prime intervals and space intervals given by v delta t prime. We see a clock in motion, so now it's not in our own rest frame. It's moving with a constant velocity. But still, this proper time has to hold. And so we get, from this minus interval here, delta t prime squared minus delta x prime squared over c squared. No, I'm putting the root here. Okay? This again is just beta, or rather I can take out dt prime squared with a square root, so I get it once on the outside. Then on the inside I have 1 minus delta x prime squared over c squared delta t prime squared square root. And this is by definition just beta. So we have delta t prime times 1 minus beta squared square root. And this is of course exactly, this brings me back to my gamma, or 1 over gamma. So I get delta t prime divided by gamma. Wait, yes, and that means if I flip it over, delta t prime is gamma delta tau, because this is also equal to delta tau, it's the proper time. So in any moving frame, time will seem to go wrong. Okay. I think you saw all of this in your whatever special activity course. Who finds any of this so far new or unexpected? You've all seen this. So now we're going to talk a little more about vectors and tensors in the way that physicists treat them. And our underlying problem will be that you all have a preconception of what a vector is, and it's wrong. Or rather, the reason it's wrong is because you all have an intuition that was developed in flat space-time, in flat Euclidean space. You guys are used to thinking of vectors as some arrow coming out of a point, maybe with coordinates or without coordinates. And your intuition tells you that this vector and this vector are the same. But you learned that in algebra, right? You can move a vector around. But that doesn't work, of course, once we curve spacetime. As we saw kind of at the end of last week or Sunday, there's no way any vector here will be equal to any vector here. They don't even live in the same space. Okay? This point and this point are completely different points. So we're going to have to define a vector living in some point of space by saying that if this is some space or space-time or some manifold, I'm going to write that word, manifold, which you can take to mean just a surface with some coordinate systems, one or more. Actual vectors that live on this surface actually have to live at the tangent space or plane at every point. So here, for example, you can have vectors like this or like this, but here your vectors will look this way. Okay, the tangent space will be different. So at every point, P, we define the tangent space, TP, and the vectors at this point have to live in that space. Maybe easier to see in 3 dimensions. At every point I put a tangent space or a plane. if we consider the Earth as the surface of the Earth as our manifold, then I can talk about vectors going north, south, east, or west, but not up or down. That's not tangent, right? That would cause me to, if someone were to go up, for example, he would leave the surface. And the tangent space is different at every point. So obviously vectors cannot be identical if they don't even live in the same tangent space. And one interesting question will be how to relay or move a vector from one tangent space to another, and from one point to another. We will no longer be able to just copy a vector from here to here. Okay. So we already had one definition, or if you want, property of a vector. We had x mu prime, our coordinate 4 vector, equal to lambda mu prime mu times x mu. In our new language, I will say that these two vectors, they do live in the same tangent plane. They're defined at the same point, but there's some transformation between them, some rotation between them. A Lorentz transformation or a boost, for example. Okay. From now on, so this is a vector, 4 vector. And now I'm going to define any 4 vector as something that obeys this equation. Or if you want, x mu changed under a Lorentz boost or rotation to x mu prime given by this matrix times the vector. And now any vector v mu will transform to v mu prime, which is lambda mu prime mu v mu. This is v, this is mu. That is, a vector is whatever satisfies the Lorentz transformation rule of a 4 vector. Okay. If I transform my coordinates with this way, the vector is anything that transforms in the same way. So what are your favorite vectors that you know transform as vectors? Moment, for example. Right? P mu goes to P mu prime as lambda mu prime P mu. And this is not surprising because P is no other than the rest mass, which is a Lorentz scalar. That is, it doesn't go, it transforms as a scalar. Scalars transform in this super complicated way. They remain the same. They're a scalar under a Lorentz transformation. Now I also have to put in dx mu d tau, but tau is a Lorentz scalar. So I have the product of two scalars with a vector, so this will be an example of a vector. It transforms as a vector. Okay. Other than this simple definition, again, note these are defined at the same point, that is, on the same tangent space. Yes?
Can you repeat that after you know tau is a scalar? How did you know that it transforms like that dx transforms like that? You just assume that?
So, delta x mu is x mu 1 minus, or 2, minus x mu 1. How does this thing transform under a Lorentz transformation? I know how to transform this, I know how to transform this. I multiply them by the matrix, by definition. But then matrix multiplication is a linear operator. So the difference between two operations of the matrix is the same as operating with the matrix on the difference between them. So then this is transformed as a vector. Multiply it by a scalar, it's still a vector. Divided by a scalar, it's still a vector. Okay? So this thing transforms as a vector. The four momentum, if you want, the energy momentum vector. Okay. Okay, so now we have at every point in space-time a tangent plane or tangent space. In our case, it will be four-dimensional space-time, so it will be not just 2 dimensions, but we'll think of it as kind of this surface tangent to a sphere. And we have our vector space. Now, at every point it is linear. We could add 2 vectors at the same point. That's fine. And you can multiply by scalars. So in general, at a point, you can have A plus B, V plus W. So these small letters are scalars, and these capital letters are vectors. And this will, of course, be AV plus AV, BV, AW, and BW. Addition is commutative. You can switch the order in addition. Scalar multiplication. So this is the simple algebra part. Okay. Every vector space has an origin. That is, we have a 0. There exists a 0 in every tangent plane or in every vector space. In our case, such that V plus 0 equals V. This again comes to no surprise. That was page 8. And another operation we will be interested in is taking inner products. But that's a multiplication, and that is a bit more complicated. We're going to find a basis before we do that. Okay. Questions thus far? Okay, so we have vectors. Now we want basis for vectors. Basis for vectors. And components. Components. Okay. So of course we want some basis where we can decompose every vector in our space in that basis. So we have to have formally a spanning set, and we want linear independence. And of course, the number here will be 4. So that's the space that we have. We can choose an infinite possibility of bases. But the dimension here will be 4 in any of them. The dimension will be the same. And an important point to make here is that we don't actually need to specify the basis, or even have to know of one, for the vector to exist. Okay, this vector, for example, it exists and it's the same no matter which basis I look at. So you have this intuition from mechanics, from algebra, that a vector is the set of coordinates, like 3 points or 3 numbers or 4 numbers. But that's just a representation of the vector, and that's precisely the thing that changes when you do a Lorentz transformation or a rotation. So the coordinates are actually secondary, and they're basis dependent. The vector is basis independent. Independent of the basis in the decomposition. Okay. So we're going to define our basis in the following way. We're going to have unit vectors, unit basis vectors, with an index mu. Note that it's in parentheses. and then it's on the bottom. Mu, of course, can be any of CT, X, Y, or Z. So far in special relativity. And I'm going to say here at each point P, equivalently 0, 1, 2, 3. For simplicity, we're going to take these basis vectors to be the simple ones, t, x, y, and z, are aligned with the coordinates. So we take, for example, ex, or rather e1, along the x direction. And similarly for t and y and z. Now the subtlety here. This is a vector, a full vector, right? A basis vector. It's not the x component of a vector. It's the basis vector called x, or called 1. So often if you write something like xi, let's say x1, you'd think that this is the I coordinate of a vector x. The parentheses here remind us that it's not. This is a full vector called x, or 1. By definition then, any vector A can be written as a linear combinations of these basis vectors. So sum A mu E basis vectors mu, which again, with the summation convention, is just mu going from 0 to 3 of A mu E mu. Now you can think of these A mu's as kind of coordinates or components. Okay, so I'm building a vector as a sum of 4 other vectors with some coordinates.
Aren't you missing an index if it's a vector?
What?
Shouldn't it have an index if it's a vector?
What, this?
Yeah.
So the abstraction I'm thinking of here is that this is the vector, and this will be the representation relative to a basis. If you want to put a mu here, what you're really saying is you want to have, you basically define the basis. Because the mu is then the coordinates relative to that basis. I want to think of this as kind of the geometric or the algebraic thing, the vector, and if you give me a basis, then I can give you the coordinates. Okay? Yes?
We only have 3 components because we go from 4 dimensions to the surface of the manifold.
No. So, okay, so if you were looking at the surface of the Earth, then you'd have a 2-dimensional space, 2-dimensional surface, and the tangent space will be 2-dimensional at every point. Okay, so the dimension of the space is the dimension of the tangent space in that case. It's curved, so it's easy for you because it's curved in the 3rd dimension. But if you're an ant, you don't know about this curvature. You live in a 2-dimensional flat space, and that's your space, and that's where your vectors live. So our tangent space of vectors will be 4-dimensional, because we live in 4-dimensional space-time. And we don't know whether it's really curved in some higher dimension or if there is a meaning to that. So 4-dimensional tangent space. Yes.
I can think about the A without the mu as like the velocity or the error or something, and mu or just a vector like a column number.
Yeah, you can think of A as the arrow at a point. That's an abstract thing. And A mu as the coordinates or components of that vector in a particular basis.
really you should just have another E with an E, and then give a. You should just give the index an E and then multiply that whole thing by another E, like another basis vector, and then that would be defined as a normal vector.
So you're trying to introduce now the concept of inner products and
no, it's not in its product over here because you're summing over those basis vectors.
yeah, I have a linear. Every vector is by definition a linear combination of the basis vectors. Right? This is just saying it's a linear combination. And the prefactors, like the coefficients in that linear expansion, are going to be the components of the vector.
They are orthogonal. Do you assume the basis is orthogonal?
So we haven't defined an inner product yet. We will eventually want to define those things. Okay, and we already gave an example of, for example, an example of a vector. P mu is the derivative of x. But if you want, you can think of any curve. If now this is my space, any curve here at any point, you can think of this curve as parameterized by x mu of lambda. Then, of course, the velocity or the tangent, dx mu d lambda, will also be a vector. Again, it's a vector divided by a scalar, and by definition, if the curve lives in our space, then its derivative will be in the tangent space. We can't go outside of our perpendicular to the tangent space. Okay, so these will be the coordinates. The entire vector will be, in this language, v mu e mu. Why is this distinction important? Thus far, we just had fixed basis vectors. At some point in the course, not very far from now, we're going to have our basis vectors possibly change from point to point, as the tangent space changes from point to point. Only because you're living in this intuition of flat space, you think that you can carry the same coordinate system across all of it. But of course, you won't be able to do that. And then these are going to have derivatives as well. So we have to remember that a vector is expanded as a linear combination of basis vectors. And if we start deriving these vectors, then we're going to have to derive the components as well. Okay. Okay. Another point on what's up and what's down. These again are basis vectors. We have them with the index on the bottom side, on the bottom part, because we want the components or coordinates of a vector to be on top. So to maintain the summation rule, these have the index on the bottom. Okay. This also means that the transformation of the basis vectors will not be the same as of these 4 numbers. In fact, they'll have, in some sense, these will have to transform opposite to the way these transform. Because if we want to transform this vector from, have a Lorentz transformation, for example, we know how this thing transforms. The vector itself will not change. It's the same arrow. So this will have to transform opposite to the way this transforms. Okay. So how do we transform the basis vectors? How do we transform basis vectors? So we have a vector, v, equals to v mu, basis vector mu. And there's an implied summation here. If I want to change to a different observing frame, I want to do a Lorentz transformation, then this will be equal to v mu prime e mu prime. It's the same vector, the same arrow. I'm just looking at this object, this v, before and after, if you want for the transformation, or for two different reference frames. I know how this transforms. That will necessarily tell me how this transforms. Right? It tells me I know that this is equal to lambda. I'm just copying from here. Lambda, I want to go to mu. Wait. Make sure I don't get the indices wrong here. Mu prime mu v mu e mu.
New prime. New prime.
New prime, yes. This is going to be subtle. Okay, by definition, v nu prime is a Lorentz transformation of v mu with a Lorentz matrix. So this is this. And this is the same. But now this is also equal to this. Which means that this has to be equal to these two. So I do that. So I get from this that E mu is now equal to the product of these two black things, lambda mu prime mu E mu prime. This might look like the transformation rule we had here, except of course that it's opposite. Because now the matrix, the index, the unprimed index is now at the bottom, here and here, and the primed was on top, here and here. So this is in fact the inverse matrix of the other one. We're transforming the basis vectors opposite to the way we transform vectors. And I'm going to write that explicitly. Lambda minus 1 mu prime mu is lambda mu mu prime. Mu appears first and mu appears second. Okay. We now have two sets of things so far, upper indices and lower indices, and they transform differently. Subtleties, subtleties, subtleties. Another thing I can say, I can take this and of course multiply by the inverse here and get the condition, or what does it mean for one to be the inverse of the other. It's basically saying that lambda ni prime mu lambda sigma prime mu is equal to delta sigma prime mu prime, right? This is by definition the inverse. This is to say that this is the inverse of that. And equivalently, lambda ni prime mu lambda ni prime sigma, or rho, equals delta mu rho. And another thing to notice here, first of all, of course, this implied Einstein summation convention with mu and mu. And the second thing is that you can think of it as canceling out numerator and denominator. Right? So any repeated index is summed over. It cannot appear on the right-hand side. So I'm left with sigma prime and ni prime, and of course, if they're inverse of each other, they have to represent the identity matrix. And so this is the identity matrix with the remaining indices, up and down, and here as well. Now ni prime is being summed over, so kind of cancelled out, and I have mu on top and rho at the bottom, and I have these identities. According to delta, of course. Okay. Just to complicate you further, Asaf likes to keep the indices in order, so you can see that there's a space here. He maintains the same order. Bernie Schutz's book uses a different convention, where he always puts all the up indices on the left, and then all the lower indices on the right. How can you tell them apart? Keep track of which ones are primed and which ones are unprimed. That's kind of the trick. Okay. So these two types of things, which we kind of intuitively think of as vectors, are really telling us that there are kind of two types of what we would like to call vectors. And so we call them contravariant vectors and covariant vectors. So covariant vectors under Lorentz transformations, they change or transform, they vary like something else. They co-vary. Co-vary with what? With the basis vectors. So these transform as basis vectors. Those who vary opposite to the basis vectors will be called contravariant. Contravariant vectors. Give me an example of a contravariant vector. X mu, P mu, right? With a mu on. Basically, if the index is on top, okay? If the index is on top, it's a contravariant index. If the index is on the bottom, it's a covariant vector, or a covariant index. For now, we only have vectors, so there's only one index per each. But we'll soon see that things can have mixed indices. Some of them will be covariant, and some of them will be contravariant. Rather, contravariant on top, covariant at the bottom. Yes?
So covariant and contravariant. These terms are determined by the way the coding is transformed.
By what?
By the way the coefficients transform. That's kind of what determines the thing. Right?
Yes.
It's contravariant if it transforms, if its coefficients transform opposite to the basic vectors. And covariant if it transforms like the basic vectors.
Yes. Covariant transform like the basis vectors. Contravariant vectors transform in the opposite way. It's a bit confusing because you would think of the contravariant vectors as being the normal vectors, right? X and P and such would be upper indices. But the reason for that confusion is, as we had here before, or as we had here, because what you're really varying is the coefficients of the basis vectors.
So the contravariant vectors, the reason they transform opposite to the basis vectors is to kind of cancel out because they multiply.
Exactly. By definition, the object is the same. But if you make a transformation, the basis vectors change. And so the contravariant components have to transform in the opposite way to cancel out the change in the basis vectors. Because the object has to remain the same. Exactly. Okay, so contravariant and covariant vectors. Okay. Just a moment. We can think of other objects in a space that will transform like the basis vector, like the covariant vectors. It won't be the tangent space, because the tangent space is the space of contravariant vectors. What is the space of the covariant vectors, or the things that vary, transform like the covariant vector? That will be the dual vector space. the dual vector space, also known as the cotangent space. So we had the tangent space, which was tangent to the surface, and now we have the cotangent, that is the space of things that transform like the basic vectors, and that's denoted by TP star, the dual space. For dual vector space, or for short, dual space. And you can think of what this space is as the space of all the linear maps from the tangent space to numbers, to scalars. That is, if you have an omega in the dual space, you can act with this omega on any vector. Bad letter, U. Here I have two vectors in the tangent space, so V and U are in the tangent space. Omega is in the dual space. And if I operate, same as saying multiply, then what I will get here from linearity is A omega V plus B omega U. The scalars just go outside. And now omega is acting on V, or omega is acting on U. And this will be a number in R, a real number. And this should start looking somewhat similar to inner products and things like that. Okay? If you have a vector in a cotavariant vector and a covector, one of them can act on each other, and you will remain with just a number, or rather a scale. Okay, so as we said, these maps are themselves a linear space. So A omega plus B eta on V is the same as A omega on V plus B eta on V, linearity. And now we're going to introduce a basis of the dual vectors. Okay, now trick question. If the basis of the contravariant vectors had low indices, what type of index is the basis for the dual vector going to be?
Upper indices.
They're going to be upper indices.
Because the coefficients.
Because the coefficients appear below, so the basis vectors have to have the index up, so they will transform opposite to the covariant vectors. So we define them as theta, ni on top, and the requirement from the dual basis is that if you operate on a basis vector, you get delta nu mu. Yes?
How did we create a basis to a basis? How is it?
I'm not sure I understand. You want a basis for the dual space. Before we had basis vectors, right? These were not a component. This was a vector living in the tangent space, and a linear combination of these gave you any vector in the tangent space. Now the dual basis, or the dual space, is a different space, and you need a basis for that. How will you find a basis for that? There will be a group or a set of covariant vectors, and they'll transform basically opposite to this. Yes?
Omega here is a functional, yes? Omega is a functional.
Omega is a linear map.
Okay.
Sometimes it's called a functional. Okay, functional. It's a linear mass. This is a linear space. This is expressing the linearity of that space, and this is expressing the fact that what is the space? It's linear maps or functionals on the regular covariant space. Because this means that this acts linearly on that, and this is saying that they themselves are linear.
Theta is a unit function.
Theta is a basis vector. It's a dual basis vector. What this basically means is that we can write any dual vector, any vector in the dual space as a linear combination with coordinates on the lower side of these dual basis vectors. Now this omega mu will of course transform as a covariant vector. Okay, so this is the object, and this is the representation in coordinates, and it will the coordinates will transform as covectors. So sometimes we just call these covectors, or covariant vectors and contravariant vectors. Okay. So of course, again, these will be the covariant vectors, and another name for them, which you might hear if you look at books like Meisner, Thorne, Wheeler, TW, they're also called one-forms. One-forms are used in some other formulations of differential geometry, Cartan formulation. I don't think they will appear further in this course, but it's good to know them. Okay. This is useful because now we have a very simple way of writing how a covector, or an object in the tangent space, acts on a contravariant vector. Right? What is this omega of V? Well, everything is linear. So omega is just omega mu theta mu. And V is just V nu E nu. I just expanded them. If you want, this formally, we can put the. Oh, we'll keep these here.
Brackets in the over V.
Yeah, this will operate on this, but I don't really care because it's just multiplication. So, of course, these are coordinates, and if you really want to put it properly, we'll put the V mu here and the theta mu here, so it operates on E. But we know what this is because that's how we defined it. We defined it as delta. So this is just delta mu nu. Notice I'm maintaining the indices in their place, the contravariant index and the covariant index. Now I have repeated indices and I know exactly how to cancel them out because this is just a conical delta, so I'm getting that they have to be the same, right? I'm getting omega mu V mu, and this is just a number in R. But I use this delta to say that this mu actually has to be mu. And I kind of canceled out the upper index with the lower index with the delta function, so I replace this to a mu. This is just a repeated index now, once as covariant, once as contravariant, so this is just a number, or a scalar in R. Okay. This is very useful because it tells us that from now on we basically won't often have to worry with E and theta, the basis vectors. We can work with the kind of simple representation of the coordinate vectors, the representation coordinates. The only thing we have to remember is to distinguish between which are up and which are down, and what is the algebra when we transform each of them. Okay, so that's why usually we talk about this as the vector or the contravariant vector, this is the covariant vector, without realizing that we're actually talking about only the coordinates, the coordinate part of the basis vectors. So that's why this is useful.
So really a vector is defined without the index.
Again?
So really you're defining a vector as being without the index. The index only shows up on components or on the basis vector.
Yes.
So
So
it's just an object with no index.
exactly. So we have two types of vectors: the ones that live in the tangent space and the ones that live in the dual space. But often, what I'll be doing, or will be doing, is looking at the representations in one basis or another, and then we'll just have to maintain which ones have an upper index and which ones have lower indices. And another useful property, of course, once we have this, is realizing that any vector in the tangent space can be thought of as a linear map operating on the dual space. That is, I can equally well write this as V of omega. The tangent space is dual to its dual. Every space, I think, is probably under some conditions dual to its dual. Yes?
Just
Pretty sure it's true. It's kind of a linear algebra problem.
What?
I don't think there are any conditions in that. It's a linear algebra problem.
Yeah, I don't want to quote whatever conditions are needed, but surely in our case, because the space is all, the dimensional is always finite and low, that's true. Okay. For completeness, what is the transformation rule for the omega mu? So omega mu prime, and you don't even have to know anything to do this. You just write whatever comes to the thing that you have to write, right? It's the law of the continuity of the board. It has to be a lowest transformation, so I must have a lambda here. There has to be an omega here, because I'm transforming from an omega. If this has a prime index, this must have a non-prime index. And if this is on the bottom, this has to be on the bottom. So I'm putting a mu here. And now I really have no choice but to keep this mu prime at the bottom and mu at the top.
And how do you decide from left to right?
It matters less in this case because I have the primes. And the primes tell me which way to go. Okay, and for the dual vectors, of course, I'll have the opposite. I'll have rho prime equals to some lambda of theta sigma. And now, which indices to put where? Exactly. I have to put sigma at the bottom and rho prime at the top, because I have to conserve the number of indices on top and the names. I have to conserve the indices on the top, and I have to cancel out these two. So that has to happen. Okay. Didn't make it all the way across, but I think we'll stop here, and Asaf will pick up from the examples on Sunday morning. Good luck.
Can I have one question?